Hello, everybody. Welcome back to our once a week podcast that has turned out to be once a month. We're trying to be better about it, but I guess at some point it's I don't know how's it in English, but anyway, we'll, we'll,
We're
we'll,
always trying.
we're trying. We'll try to get it more, to have it more frequently. Ideally, I'd like to have it at least once a week. It actually went on like for once a week almost at the beginning. But I just recently heard a statistic that 90% of podcasts end before the fourth episode. So we went past that mark, which is good. And also then after that, 90% of podcasts stop before the 20th episode. So if we get to the 21st episode, then we're we're in the top 1% of podcasts. Not
Sounds
by
like a
viewership, most likely, but at least by hours of podcast material.
sounds like a commitment. So we'll talk about it on the 20th episode to see if we'll continue or not.
Yeah, year 2024.
Yes, that is also true.
With the current trend. But anyway, if you're a avid watcher of us, you know I am Josip Klastik. I'm a PhD student in the space technology department in Tartu, Estonia. With me is Hendrik, who is
Who is doing robotics at an autonomous driving company called NeRF Robotics. It's actually a military company, and also a PhD student at University of Tartu.
So today we have a topic picked by Hendrik. So currently how we do it is, let's say once a week, Hendrik picks a topic, once a week I pick a topic. So Hendrik, I get, you can introduce the topic we're looking at today.
Okay, so NeRFs, a hugely kind of popular and very new thing in the field of computer vision, mostly, where the goal is to basically generate 3D structure of the world that is very visually, like from camera images, create a 3D structure of the world that is very similar to real life, so very photorealistic. And the method that they used to do this, which this kind of original paper originated, called NeRFs, is by training a neural network to do this kind of conversion to use a neural network to learn this kind of 3D structure of the world. That's like the main intuition behind it. However, well, of course, the specifics are very important and how kind of all this process is set up and so forth. But first off, I think that's the most important thing is that this neural network basically is able to hold this 3D structure of the world, which is already quite cool in and of itself. Basically, that this you are able to teach the neural network to do that. But of course, there are some kind of specific reasons why and how it works. So we'll get into that.
And
And
as,
what? Yeah,
sorry,
go go.
I want to say that as we can see from the title of the paper, it's or not title, the subtitle, I guess. It's from cooperation between Google and UC Berkeley. I think it makes quite a lot of sense why Google is researching this. So if you put this together with their Google Maps, so currently they have the cars driving around, they're making pictures, and so you can plug your person down in the app and look around. And I think they want to make that a lot more interactive. That would be my guess why they're leading into this research.
Yeah, I think it like the applications and use cases will be interesting, and there are some blog posts in the bottom that has some references to kind of in which directions these things are going at the moment. But once again, I think there are a potential of use cases are quite many, but it is in some way a bit of a new paradigm compared to maybe other similar methods used before. So I guess we can get into the details and start exploring these kind of pros and cons and what it actually does and how. pretty much. And interestingly, you mentioned that this kind of collaboration between a university and Google Research. It's always interesting to watch that. Every time you usually see this, then this first author, of course, now works at Google. So
Yeah. Yeah, I was actually watching, so preparing for this, I was watching, I think, from one of the authors also a video on the subsequent papers and this paper, and he also, before, he used to study at UC Berkeley, and then he went to Google, and he's been doing all the stuff at Google, and now they have a relationship between UC Berkeley and, of course, and then you can get, I guess you can get a lot more money at Google than UC Berkeley.
yeah, for
10,
research missions.
10x most likely.
Yeah. Well, that's just how it is.
Yeah.
Starting off, let's get into kind of what the paper presents.
Mhm.
So the paper basically presents a new way of basically not necessarily a conceptually new way, but basically using these radiance fields as the main thing to basically store information about this 3D structure and what like the thing that you train for. So what this is basically a function that if you place a camera in the world at some specific coordinates and watching in at some direction, then this function basically outputs the well, yeah. So it not well already. So basically, if you put a camera in the world, you trace a ray from the camera, then at each point in this in the space there is something. There is a function that converts the position pretty much to color and opacity. And if you accumulate all of this information from the ray together, then you get basically color, which you can then use for actually rendering an image that you're able to see from the camera. That's like the high level view, but I guess we'll get into how in a second, unless you have comments.
And I guess we should say what is a radiance field.
Yeah, well, that is kind of it. So that, but I'll scroll to images to explain it better with, I think, images. So I guess the bottom one is a good way. I'll zoom in a bit. So it is like the leftmost picture basically describes so radiance field is this function here, which kind of takes in these this kind of location in this 5-dimensional space, and then outputs this RGB opacity value at each of these points. So that's kind of like how you can use like that's the point of a radiance field. And well, the kind of the goal of what we are trying to teach the neural network to do is to become this basically function in between.
Yeah, so the idea is that like in the most general sense, the idea is that we're basically imaging an object at different angles, and then we can just specify like random angle, and then or we can just like move the camera around, and it would generate new images of the object, the whole algorithm. So that is the main thing, the most general way to say, I guess.
Yeah, and effectively that kind of becomes like you moving around this camera in this world basically is like equivalent to you kind of being in this 3D structure of the world and basically putting this camera in different locations in the 3D structure, and then you get like how would this look like from this different angle that you didn't have at like when you actually took the initial images.
Mm-hmm. So logically, the neural network has to do a lot of work, so it has to understand, it has to put together like that the color at different images is this is the same point we're looking at. So
Yeah, and
there's a lot of work to do.
yeah, and in some way it has to be like a 3D structure, because like you move around in that environment. So if you look at it from a different like angle, then it has to kind of work like a 3D structure. So it actually has to in some way hold this information about the not kind of directly, not as a concept, but basically needs to hold the information about the how the 3D space looks like.
Yeah, actually, they showed in their videos they realized that basically depth maps that come out of this same thing kinda, and then they had this really nice example of they had this ball and they moved around and it went like they showed how it understood that should it be behind something or in front of something depending on where it is, so it has to learn all of this.
So yeah, basically, initially, like you don't have any information about kind of where this object is, kind of from the like from this distance. But then they use this like approach that you kind of basically these different positions on this, let's say, camera array are all, let's say, initially like are all like it's possible that on at each of these points there is some kind of an object, pretty much, right? But of course that does not work out if you have well, you could imagine like the initial weights are so that it is possible that objects are everywhere in the world, pretty much. But there is like a unique solution where if two cameras from two different angles see the same object, then it has to kind of like these camera arrays like have to see these how do I call it, objects, or these whatever surfaces of the object kind of from the so basically if you image with multiple cameras the same point in space, then that's the reason why this neural network is able to learn this information about the 3D structure, because if you initially assume that this object is at every point in space, then over time when you train it, when you have many like these camera views and you gradient descent through this neural radiance field function, then it converges to this basically 3D structure of the world, and then basically that's where you get your loss from. That's where why you're actually able to use these neural networks at all to basically find this function.
It's actually quite. I mean, the training seems, in that sense, quite easy. If you have like a 3D model, it's always easy to generate a new viewpoint and compare it to the ground truth. So in that sense, it's very easy to train.
Yeah, well, yeah. So you basically sample array and you see does it match basically the reality. But you can't, let's say, your learning data is still this these initial images that you put in. In that way, you don't generate like a new unique view from a random point, but you give all of these cameras in. But one important limitation that is actually mentioned quite at the, let's say, end of the paper is that you need to know these positions of cameras in space to do this thing. There is some research where they also are kind of automatically finding the positions and orientations of the cameras, but it is a much more difficult problem to do those two things simultaneously, pretty much. But yeah, fundamentally, use some kind of a structure from motion algorithm, which is a way to find. Let's say you take a picture of, let's say, 50 to 150 images of your, let's say, room that you are in. Then you run it through a structure from motion algorithm, so you find where all of these pictures were taken, or you use a simulation and you get the same information out right from the simulation. But in real world, you need some kind of a method to find where the camera was and where it was oriented. And then you put this information into a NeRF, all of these cameras have a pose and an image, and then we can start training. We sample kind of rays from these cameras. We see kind of how well it matches the all images kind of like how well does this model match what is actually on the images. You get some kind of a gradient, you descend toward gradient, and next at each iteration the generated images start to look more and more like the actual images that you have taken with your cameras. And after you have done that over and over and over again, then let's say this 3D structure emerges pretty much, and then you can move around in the space because now it basically holds the information about how it looks in the 3D structure.
I guess we should also say this isn't the first algorithm to try to do this reconstruction. They show quite many comparisons to the, let's say, the state of the art before, and they look quite bad. All of them. I think this is the at least from what they show, this is the only one that looks good.
Yeah.
Yeah.
Here it describes a bit about this input images and poses on this view, and then you are able to render new views, not only from the initial cameras, but basically from wherever you want to in this structure. This importantly is like a simulation image. So here they have these very exact poses. Every time you have, let's say, less accurate poses, that actually affects the result a lot. I did also like a small experiment at on my own room with and the second paper that we will show before, but basically the GitHub instant NGP, which is made by NVIDIA, and there also it's very important to have these camera poses accurately, and that's like actually one of the more difficult problems in the real world scenario. So these look better than most likely the real world scenario would in this case.
Because in simulations it's really easy.
Yeah. Pretty much. And theoretically also like the simulation images might be easier. Depends on how they are kind of made.
But I saw that because this paper is old, because it's already like 2 years old, so it's like prehistoric. So they have a lot of quite a few real world examples as well, where they just basically what it seemed to be they basically took images of Google. They removed all the transients, which means everything that isn't always there. So, for example, if you're looking at the Tower of Eiffel, and there are in every picture there are some kind of people, so they first do like pre-processing it, so they remove the people, or they let the neural network know that the people aren't important, and then they get quite nice reconstructions of actual landmarks as well.
Yeah, it's definitely it is definitely like it works also in the real world. That's not a fundamental limitation, definitely. It needs this additional component to figure it out. They noted their contributions as well. First, this basically using this neural radiance field concept that we talked about. That this is like a better structure for basically solving this problem, as others had tried with different other, let's say, volumetric and distance fields, different, like say, functions to also represent this 3D geometry, but those kind of approaches were definitely not as successful as using this this method. Then they kind of described a bit about the 2 and 3 in my mind merged together a bit. So it's like this how they actually kind of sample this space, basically like these camera rays and like ray marching techniques of how you actually kind of are able to how do you put this, understand like where is this intersection actually with this object, and kind of what does it actually mean, like the fact that each point basically represents some kind of and each of these interactions also has some kind of opacity, So that means that every time it like goes through something, it also has some opacity. So some of the kind of a part of this basically irradiance goes through this point also. So at the start, it's like a cloud, like a dust cloud or something, like a cloud you can see through, and then it kind of converges to something where you have some objects that are, let's say, no light goes through them, and then like free space that lets all the light through. And the second important part there is this positional encoding, where if you just did what we just described, then the result would not be very good. What I mean by that is that they pointed out that this kind of positional encoding, where instead of just using these 5 dimensions, so these positions and angles, they put this through some kind of an encoding method that basically generates more data from these initial five coordinates. It had something to it's like some kind of a it is in some way they brought out that this is analogous to how transformers do things. I did not quite fully figure out how this one-to-one relation, like how this encoding exactly works. But they brought out that this is pretty much one of the most important reasons why why the neural network is able to learn these higher frequency data, basically. So like small details and stuff like that.
So
Yeah.
so like I said, I also watched a video where they talk about their subsequent work, and so when they were doing this paper, they understood that this works. They didn't understand why it works. They were like, we don't know, but it works, so we're just gonna put it in. Like they first wanted to like understand why it works, but that took too much time, so they just put out the paper. But they have a whole paper on this, and I didn't read it, but from if I understood correctly, basically, so what the position encoding does is for each degree of freedom you have originally. So let's say you have the XYZ coordinates and the angle. So you basically take one coordinate, and then from that one coordinate you do you have the equation here as well?
No, but I can open it up quickly. I know it.
So yeah, so basically you take this for each coordinate you do the same thing, but for one coordinate you create different
You didn't think about
polynomials basically with the specific
yeah, this one.
yeah. So you create these polynomials which are the different sine and cosine functions, and so you have to choose. What you have to choose is how many polynomial or how many of these I don't know how many of these how many of these encoding tokens or whatever you create.
Yeah.
So this is this L, and what basically what I've understood is that the larger the L is, this basically means that it will take less information from far away pixels. So what happens is that if you don't have this encoding, then for each pixel you basically take information from the whole image, because this is a multi-layer perceptron. So they talked about something about MLP being just like a big kernel actually, but that is something that I didn't understand, so I'm not going to talk about that. But yeah, basically, if I understood correctly, so you have this degree L. If it's larger, then it takes more information from nearby. If it's smaller, so basically if L is 0 and you don't do this deconstruction or this mapping to a higher dimensional space, then for each pixel you take information from the whole image, and then you get this really smoothed out features. You don't have any high frequency information. I guess it's a reason because that's an MLP. I wonder if it would be different if it was a CNN, because then you don't take you kind of don't take the information from everywhere anyway. But also this was also one of the most interesting parts for me in a sense. But yeah, if you go really high, so let's say like L, I don't know, because they used L10 in the paper. So if you go to like L100 or something, then you get a really noisy image. You can basically start overfitting the train data. So that is what is happening. So they had these graphs, which basically, if you had L is 0, then it took all the it was like this very slow drop off. You take all the image, but if the L is very high, then you get this really nice peak, and then you have to find the trade-off, how much you overfit, and so you basically have to see in training and test data, see how well you fit.
Yeah, the interesting part is like this NVIDIA's instant NGP pretty much does the encoding very differently. And they called this positional encoding, I think they called it, just to make sure, I think they called it frequency encoding.
Same.
Because it's like, because it's almost like some kind of a Fourier transform in some way.
Yeah, that's what they were talking about actually in the subsequent paper about Fourier transform. So they said that if you add this, you basically create a stationary kernel. Stationary should mean that basically it's shift, I guess, invariant to shifts. Or
yeah, that sounds like it.
I don't remember.
Sounds like it.
I don't remember my maths currently.
Yeah. Invariant to translation. Very fancy words.
Yeah, shifts.
But also known as if you just move it, it doesn't change.
So yeah, a stationary process is a stochastic process whose the joint distribution doesn't change when shifted in time.
In time, okay.
Yeah. So basically, so that should mean that so in time we can mean that within the different frames, I guess. So the information doesn't change if you take the different images, kinda. No?
Not sure. I'm not sure if there is one-to-one relation there because of the yeah. I'm not sure how that relationship with time would apply here. It does not seem to apply. Unless you read that from their paper.
I'm just reading from Wikipedia what stationary process means.
Yeah, I think that might be something slightly different in this context. I would assume it to be. Stationary in some other dimension.
The process is stationary as its statistics are constant, frequency and everything. Okay, anyway. So basically it's basically you're injecting an implicit bias that things shouldn't. I mean I still kind of think like you're basically putting an implicit bias that things shouldn't change when the underlying information shouldn't change when you're looking at a different angle, I guess.
Maybe. Okay. Yes, but you don't necessarily need encoding for that, right?
But apparently you do. But yeah, but it's weird. I mean I should read the paper, but because when they talked about how it works, then they talked about how many what kind of information it takes in from the whole image at that point. So it's a bit different. So this
is I mean it's like I understand that part of take information from the image. You can kind of imagine it like how do you kind of get this radiance that you actually like see when what is the actual camera, like you have this camera pixel and you need some kind of a RGB value there, right? And like how do you add these different, let's say, irradiances pretty much together? And it turns out that if you put some kind of a like instead of just taking all of these points in like on this, let's say, camera array and just smashing it together, apparently in this way, you kind of filter out some kind of information. You smooth it out pretty much. You make it now. Now you make it higher. Like you make some kind of higher dimensional structure. You put that inside of the neural network. So the neural network smooths it out. And this also applies for not only this problem, but this is like a general thing with neural networks. So it kind of smooths this type of information out. And if you go put this encoding, which is higher dimensional, then it is able to actually learn, let's say, patterns about, let's say, higher, like that apply to higher frequencies. And yes, it does have to be consistent from different, let's say, angles. That is true. This kind of same function, the same pattern in this kind of direction has to apply from different angles. So in this way, it can still represent like the same 3D structure information, but part of it is now held in this frequency domain, or quote unquote frequency domain, because we want to actually get this high frequency information out of it.
Actually, now that I remember it, if you show me this, because I think they basically did in the next paper where they talk about this, yeah, they do it a bit differently than here. I think why it's stationary there is because in here they only use this L, right? But in there, they actually, for each of these parameters, they take a random parameter from normal distribution into here as well.
Okay, yeah. I think they.
Or is this the P, pi and P, or is it what is the P part here?
They should also be sampling here. Or now I'm thinking if I'm getting my papers confused or not, because it definitely was in one of the papers. This one.
Yeah. But this is for the this is for the remarching, isn't it?
Well, yes, but in some way it is kind of related of how.
I wouldn't say
Okay,
so.
so I think it does not necessarily need to be related, but it like so your point is that this kind of how they choose points in the space is also kind of used in the positional encoding in the future papers, or
Yeah, they were just like trying to figure out why this encoding works, and
yeah.
and in there they, if I can just find the paper, they had it. I don't know what the P is here. Does it say what the P is?
You mean this P here?
Yes.
Did
Let's see.
not
Which is normalized to line -1 to 1, and the free components.
well, the position is P.
Okay, P is the X or Y, or is that?
Yeah,
Okay,
yeah.
okay. So yeah, here they don't have any stochasticity inside, but
Okay, later they have it here also. Okay,
yeah,
interesting.
if hope I'm not talking about out of my ass. I will, while Hendrik talks about stuff, I will double check
Okay.
myself.
I mean, that is completely a reasonable explanation because of if we look at this. Well, here they have the same one, basically the space encoding, but they moved to very, let's say, a very different encoding on the in this NVIDIA paper. It's like a hash encoding, but they did talk about, I think, the problem that you described. Mostly about this, basically, pretty much the same problem that we have been talking about. That this kind of coarse resolution versus fine resolution, and I guess the balance between them, and how do you actually figure out kind of what you should use? Because this is in some way, as it's mentioned here, it's kind of like it's like almost like an hyperparameter that is like the balance between coarse things and fine things, which is like how much of coarse detail you have and how much fine detail you have. And I would assume that the follow-up was kind of learning that information also then, or I'll have you find it out then. So yeah.
So anyway, so something interesting maybe that we can look into at some point, because I want to understand about it. So that they basically say that how neural networks are actually is just kernel regression, but it's just like a very massive kernel, kind of, and yeah. So if you use so I guess this is a good podcast if I'm quiet.
Okay. We can move on for now and get back to it, because as we mentioned, I think in the start, this is NeRF 1. There will be most likely more NeRF discussions following on. So as we learn more, we will add corrections to everything that we have made mistakes in. So, but fundamentally, I think we can move on from the let's say the initial setup or description of these of the, let's say, concepts that they use to get these great results. Yeah.
I will send you a paper. If you look at page 7 of that paper.
Yeah,
so this is their subsequent paper, which we haven't read. So the name is Fourier Features Let Networks Learn High Frequency Functions in Low Dimensional Domains.
It sounds exactly like it's more general than only NeRFs, which is reasonable, because I think these concepts are actually
because
larger.
If you look at the figure before we go to page 7, if you look at the first figure there, figure 1, you can see that. So actually, this is why it was very interesting to me, is that they use it in different things, just like image regression and MRI reconstruction, and everywhere it like added good stuff. So I was wondering if you can use it in super resolution, but I guess it's a bit different there because you have CNNs. So, but I don't know.
Well, when we get to the instant NGP paper, then you will see how it is also a part there.
Yeah.
The instant NGP paper has 4 parts. One of it is only NeRF. One of it is very high resolution images. So we can talk about it there a bit.
But yeah, if we go to page 7 now, they just talk about different mappings that you can do. So I mean, of course, you can use different encodings, right? So they have this kind of basic, then they have this position encoding, which should be something similar to what they used in that paper. And then they have the Gaussian one that I talked about, where you actually take where you sample from the normal distribution. And then you basically choose the sigma or the variance, and then you can see that if you go like a bit lower, the Gaussian actually worked the best, which is interesting in 3D NeRF. Everything. No, anyway, this is a paper that we can look at some point.
Definitely. Anyways, what very importantly, I think the most important, let's say, intuition to take away here is the encoding part is critical, important, one of the most important parts. You could once again make this connection to transformers, where pretty much the transformer is this like an encoder-decoder part that you train in their case, but still.
Yeah, it's basically useless without the positional coding. Do you have any figures here where they show the comparison. So they did some ablation
Ah,
where they took out the different parts, and we can see if they remove position encoding, it basically becomes
yeah, this one.
you see
Yeah.
it becomes useless. Well, not useless,
Yep.
but near useless.
But yeah, like how like the fine details get smoothed out pretty much. Is the main point.
Yes. And it was quite interesting for me because my first thought when I was reading this, like, just I guess you can just use a bigger network. That was my first thought. Because I mean, that's how you get higher frequency. You just let it overfit more.
Maybe possibly.
But I guess this is a more optimized way of doing it.
Yeah, and where they mention it, it's like this to do. Yeah, here I think. Wait. No, not this part. Don't find it right away. Where they discussed this same thing. They didn't explore it like a lot, but they just pretty much also said that this is we can go to this figure 4. No, they actually they talked about it higher up. Here they mentioned this connection to transformers. Yeah, they say that it helps to get higher frequency information. But yeah, they don't necessarily say that you can't do this with, let's say, just add more layers way, which is obviously less efficient in this context. That's not a question. The question is, does it work in like that or not?
Yeah, because I'm just thinking, because already if you have like an image and you're using MLP, then you need. I mean, even with these small images, which were like 800 by 800 or something like that. So if you're doing less than 64,000 neurons in the first layer, then you're already like compressing data. So I would guess that. I mean, it seems kind of a weird choice to go with MLP, but I think
Yeah,
there are
but
reasons.
yeah, I think the follow-up papers also do
Yeah,
use like these full neural networks in the like in this like this even where they optimize for performance, they still I think as far as yeah.
yeah. Actually, with the performance part, there is a paper by Microsoft where they do like 200 frames per second. NeRFs. So I guess this is quite slow if you want to for each image. But yeah, this is like ground zero. Of course, it's slow. Doesn't matter.
Yeah. So once again, this was the like the where we get back to it. It like with all of these papers. Once again, I had the wrong one now. So like with this main paper, like with all like such papers, like it had a very kind of revolutionary effect. So this is like August 2020, and then this next computer vision conference. I don't remember what the name was. This four-letter abbreviation. There are so many of these.
See.
They had they ICCV or whatever. They had 30 papers about this topic, and now in 2022 they had 50 papers about it. So it's like
Boom.
somebody does it something in like August 2020, there is like holy shit, and then there is like a huge flux of papers with everyone like using some ideas that they have had previously to generate a lot of novel results out of it, pretty much. So that it had some very important fundamental thing that everybody was like, oh, if we use this as a baseline, this kind of this main, I think it's even the contributions that were pointed out once again that this first up this neural radiance field concept, storing information in these radiance fields, and this encoding concept. So those two things together pretty much seem to be the main thing why these NeRFs perform such cool things. And as they say, kind of like this first kind of neural network model that is able to do basically generate photorealistic novel views.
Mm-hmm. I mean, yeah, everything looked very bad before this.
Yeah. But now it's like the whole internet is full of stuff where, like, and once again, I also for fun used it on my kind of home a bit. Although I didn't have a very beefy GPU to train with, so I couldn't use a lot of images because my GPU ran out of memory. But still, you could see it like conversion quite well, and I also did not give it very good images. So I'll talk about this later when I show a few images.
So I guess we've talked about like how they have free contributions. We've talked a lot about now the positional encoding. So I guess I think we haven't talked a lot about, that much about the ray marching part. So
yeah.
so that was also interesting. Well, I mean, it makes sense how they do it. So they basically have two neural networks that they're training, I guess. Or was it two outputs?
Uh, I'll pick it up. Not sure if I copied it here, just so we have the text in front of us and we don't say wrong things.
Yeah. So while Hendrik looks for the correct page, so the basic idea is they have an output of like a coarse output, and then they have this fine output. So what they do is when they do ray marching, like Hendrik said, what their idea is for each pixel to find out how far is actually the thing we're looking for, the object, and then you want to sample it close to that position. Otherwise, you're sampling it from everywhere. I mean, ideally, you can sample it everywhere, and then you know exactly what the picture should look like. But that is computationally quite difficult. So you're trying to find some kind of heuristic to do it faster. So there are a lot of, I guess, a lot of these techniques come from ray tracing and path tracing, which is very all the hotness currently in the video game world. And here they do this very coarse, so they do some random sampling in a coarse setting, and from that coarse setting they get this they get information on where they should do it finer, so they get more exact information at where they should be looking at with their finer output, so to say. Was that about correct?
Yes, and this is very important because once again, because at the time step 0, you don't know pretty much anything. So you don't actually know where the 3D structures in the world are just if you look at the image, right? So you need some kind of a pretty rough thing that isn't very exact to just get like some basic 3D shapes about the thing that you can actually now go into a lot more detail with. Because I can definitely imagine that it's quite hard to start from this zero point and start like descending to anything, let's say, reasonable. Because you have, let's say, a cloud of randomness, and you need to actually find some kind of structure that you can actually in some way ray march towards, right? Because initially it's just at every point you accumulate some random amount of some random RGB values and with some random opacity, and just it goes through this kind of random. It generates a random pixel output here on this image, and then over time you generate this like this ray marchable structure that you can actually say, if my from this point to this point, there is nothing in between. It doesn't give almost any kind of irradiance to that pixel, and then at this point there is some kind of object. It is basically you don't see through that object at all, so you basically get all of the radiance from this this object that is in this location in this world, and that you can get then kind of figure out the exact RGB values and etc. Yeah. They also talk a bit about this. At least they talk about in the higher part about this that it is also quite important that you don't just do discrete, let's say, points at each point, because then you get kind of some weird discretized effects. So, but it kind of all of these, like these points where you actually kind of choose these camera array points, they are also random. So from this randomness, you actually get this continuous function, not kind of some kind of a discrete step at which kind of this information about light is gathered.
So yeah, they talk about that it's like similar, has a similar reason for existing as importance sampling. So I mean I have to, so maybe Heather can reprocess this sentence for us all. Or so basically what they say is, so if you don't know what importance sampling is, you basically try to sample that. I don't know, it's the same idea. You try to sample at the important parts, right? That's what it means. So they have this sentence here that it addresses a similar goal as importance sampling, but we use the sampled values as a non-uniform discretization of the whole integration domain rather than treating each sample as an independent probabilistic estimate of the entire integral. So I don't know, Hendrik, can you kind of
intuit it?
Intuit it?
Yeah. So basically, as I understand it, the course. So the they take both these fine samples and coarse samples, and they combine it together, not using one or the other. And the importance sampling, as I understand it, comes from the fact that this coarse network basically works as the kind of focus on this part, as in focus on this structure, larger scale structure, where the fine then, and that is kind of the importance, or that's kind of, it directs where to look at, while the fine gives the detail.
But this also, with the course, directs where to look at. That's how I understood it. But I guess it's just the way how you use them in the end, how you use the course and fine samples.
Yeah. So basically, first you get let's go a bit higher. So first you have this course network.
Yeah, we then produce a more informed sampling of points along each ray, where samples are biased towards the relevant parts of the volume.
Yes, so that's where you do the part where if you already have some kind of information about the volume, then of course you sample around that thing. So in some way, like ray marching, if you know what ray marching is, it also kind of does that. It does that just based on the fact that it finds the closest. Like you shoot the ray and you start seeing, you draw an expanding circle or sphere in 3D, a sphere around this each point, and you see how far away this any intersection with any object in the world, where it is, and then you kind of you place the next point based on this distance that this intersection happens, and this helps you to get, let's say, very close to where this actual intersection happens. So in some way, this ray marching algorithm is also kind of like, how do I put this, finds intersections. And as I understand it, they do the same thing here in this coarse network. They basically, the coarse network also is biased towards relevant parts of the volume. So it also kind of, the coarse network also works on the areas of the volume that have, let's say, then I guess in this case, lower transmittance, so lower opacity, right?
So that's the main goal to find, right?
Yeah, yeah.
But I like the sentence that they have here, which is right below equation 5, is that normalizing these weights produces a piecewise constant PDF along the way, which is just like a roundabout way of saying it produces a probability mass function, which is discrete, not not a distribution function, kind of.
Okay. I didn't follow. You can repeat that.
So they have the like. So what they say is like we use this. You do the coarse sampling, right? You get
Yeah,
this. You basically get this. You get this kind of distribution. So basically, you have the samples, and then you
yeah,
start understanding like where the fuck what is, right? And
yeah.
then they say that from this they create a piecewise constant probability distribution function, which, if I understand it correctly, a piecewise constant that it's a discrete distribution, right? Which basically,
Well,
which
yeah,
if it's piecewise constant, that means it moves in steps because you have discrete sampling, and
yeah. Yes, and
which means it's a probability mass function, not the PDF. Because
it,
a PMF is discrete PDF. If I'm
okay.
correct.
Now I understand what you mean. Yes. Well, I still like the PDF word more, but I guess that piecewise constant PDF means PMF. Okay, I get that. But yeah, they do, like, of course, like, it's important that they normalize it. Otherwise, the kind of,
Mm.
based on the amount of samples, you would get more color. So you normalize the weights, so you get like you integrate this colors over this PDF, and then you get kind of this.
Yeah, and once they have this new distribution from the course, then
Yeah,
they do new sampling based on this course distribution, and then
yeah, yeah,
they use a union of the first and second set of samples. So they still use both of them to
yeah. Okay.
get the whole image.
Yeah, that's I guess.
And then it still
Yeah,
comes to my question, if I to understand this correctly, what is the difference between importance sampling and uh, this kind of sampling? So they values as a non-uniform discretization of the whole integration domain. So they don't treat each sample as an estimate. They take all the samples together and they produce an estimate. But I guess in importance sampling, each sample itself is already like an estimate of the entire integral, kind of. Or I don't know. I don't know if I still understand this.
um,
This like this a math sentence that you have to read and think about for like a half an hour.
yes.
Or if you're smarter and better at maths than me, then maybe you understand this from get-go. But I'm not.
Uh, I
I'm,
also, I'm struggling. I think it has something to do in this context with this NC plus NF samples.
okay.
Um, so because you keep the original samples and you keep the kind of samples that you take from this new PDF, right?
Hmm. And even here they say a non-uniform discretization. I don't know it. Uh, but okay, doesn't matter. So if you're watching this and it's easy for you to understand what this means, then please subscribe, and write a comment.
Comment. Yeah. I mean, yeah, it would take a bit more detail, as we did not, as I did not focus on this specific part before the podcast at least.
Yeah.
Yeah.
But
Now, yeah, go
I
on.
think these are the most like important parts of the paper, and we can show just you can make sure you can show some results.
Yeah.
We already
The,
shown a
yeah,
bit, but
yeah. Quick comments regarding this. The structure promotion is done using a package called CallMap. You could use others also, but this is what is done in here, this paper, and also in this instant NGP paper. They also mentioned a bit that they used NVIDIA V100 GPU, and it took about 1 to 2 days to train the results that they got. The optimization for a single scene, so one kind of let's say one result that you get from this, for example, for a ship or a Lego, that all of these things, each scene takes about 1 to 2 days. So in the original paper, it does take a reasonably long time, but at the same time, the goal here is first time photorealistic thing. So it's not about performance at all yet. So it's just to show that we can actually get photorealistic things at all. And here so here is the, let's say, the object, so the simulation ground truth, and the from the simulation ground truth, the different methods are asked to generate a view from a view using like you have some input views, and they generate this model that then is used to generate views from specific camera angles. And I will zoom into now to each set of pictures. From the bottom, you can see the ground truth is on the left. So the ground truth is generated using a simulation, and then there is the NeRF. Then there are some other methods. I did not go into what those methods were exactly. Did you? So there were some different approaches with neural networks to represent the 3D environment. They just weren't very successful at that point yet.
Mm-hmm. Yeah.
Although having said that, like these other things have also looked impressive in the past, probably. To people in YouTube videos and such, but then NeRFs took over. Now our expectations have changed.
At least for me, this seems the first usable one.
Yeah.
Well, I guess every paper has their like edge or like their use cases, most likely, where they're actually usable. But for this, actually seems usable.
Yeah, well, the NeRFs had the problem at this point in time, of course, about the computational problems. But I guess we'll get to that quickly also, to just give an overview of how you can use it, and like the Syncent NGP framework also, because I think it's the most approachable for people just try out things. Anyways, if the screen resolution is showing anything, then you can pretty much see a very similar results between the ground truth and the NeRF one, and a lot of artifacting and visibly like lost information and so on and so forth by all the other models, which is quite interesting. And it kind of seems intuitively that there is like very few places or details at all where the other methods are superior to this NeRF thing. So it, in some way, it seems like the NeRF approach fundamentally like is able to like in some way like fully represent the environment. Maybe it just would need more data or more let's say some more small tweaks on the algorithm, but fundamentally all of the, let's say, features and information is there.
Well, that is a bit of a strong.
Yes, but I will qualify it like that. If you look at this like this image, so all of the, let's say, shadows look very, let's say, intuitively similar. While if you look at the other methods, then here you can see some like very different shadows. Here you don't have the, let's say, the fine detail structure, and like the reflections and stuff like that are quite like this. Just creates a lot of artifacts on the. So maybe it is in some way just like similar, but just worse. I'm not sure about that. Maybe I would say the same thing about this image.
Mm-hmm. But yeah, I still saying all the information is definitely.
Yeah, I think fundamentally it is definitely not all. So it does not. I don't know. fully simulate light transport. So in that way, that is not the goal of this this type of or it is definitely not the goal of this model, these models, to fully simulate light transport, because, well, even like I think it is fundamentally neural radiance fields are not able to do that. So because they don't have enough parameters about the materials that are used. Basically, just you have opacity and you have color, pretty much. So you don't have, let's say, a lot of other parameters that you would need to learn in order to basically simulate light transport fully. Which is an interesting point to wonder if what would happen if you'd also try to train for other stuff. But I guess it's like impossible to know, because our cameras really don't, or might not be very easy to pick it up just from the environment, because you would need to really model the light sources and how light interacts and so on and so forth to fully understand this part.
Yes. Okay, but I think we can move on to the instantaneous. So this was I guess we can say it was a nice paper.
Yeah, I actually liked the paper a lot. Actually, it was quite nice to read. It was understandable, especially like you needed some extra context, but I think also it kind of was very information dense actually. So they had a lot of stuff there. It was backed up, and I guess people also supported the fact that this kind of it makes sense to do things like this, and B, they have very cool results, so we want to use this, and they were able to set up ways of setting, like they were able to set this thing up for themselves also very quickly based on this paper, because suddenly like everyone did this. So I think that kind of shows that also. Now, instant NGP, why I also wanted to talk about this paper in this context is, this is a few months ago, or 1.5 months ago, something like that, released a GitHub page with a paper where the kind of easy way to say it is like, if before like NeRFs seemed like a research problem, now you can just take this kind of NeRFs and use it on your own thing very easily, very quickly, and so on and so forth. Because it is like a few orders of magnitude faster than other approaches. You mentioned Microsoft, so I'm not looked into that one, so we can talk about that in a second. But they claim that it's like a few orders of magnitude faster than, let's say, at least the space approach. With their main innovations being a new encoding method, and also just a very highly optimized CUDA implementation. So those two things together, basically, just so their encoding is not like the primary reason why it's those both parts contribute significantly, and I can show the table later on why they claim that. So they also tested this frequency approach only, and then they like frequency plus CUDA, and then they do the new this encoding function and CUDA, and they showed that that gives the best performance.
So just to understand, so it was trained for 1 second. So is the speed in the training part or in the recreation part?
So 1 second training, yes.
Okay.
So it basically is like you have the so you launch the instant NGP, and in a few seconds you already see like the structures if you give it very good input. If you have more noise input, so my home done with like a shitty camera, and I moved some things in between, then it's a lot harder. But
But if you move the camera around, what's the actual like FPS you're getting?
The rendering is also, like say, relatively fast, but the rendering depends also on the resolution you want to render at.
Yeah, of course. Yeah.
So on the instant NGP side, you have this dynamic resolution. So you can, if you want more detail, then you put the dynamic resolution FPS lower, and like if you want less detail and you want more FPS, and so you just get a smoother, let's say, picture, then you can do that also. For me, the biggest limitation actually was rendering. So the rendering was like the model actually holds more information than I was able to render, because my I have like this it's a laptop GPU, and B, it's like not, it's like one of these I think it was say 4000 or something like that on the laptop version. So it's also not that great, like it's not that oriented to rendering pipelines as, let's say, computer graphic cards are. So basically, like, would like to try the same thing out with a kind of 3090 or something like that, to see like how is it actually limited by rendering or not. But yeah, rendering the scene is also, let's say, quite intense. But here, so they mentioned the training times, and then after you have trained it, you can stop training and you can move around in this space, and it's relatively smooth. And if you want to see more detail, you can put lower FPS. At least that was the case for me, my computer, because once again, it wasn't that beefy. It's on laptop. But yeah, so importantly, they cover in this thing, they cover 4 different, basically neural, they call it, I think, was it training of neural graphics primitives on a single GPU for multiple tasks. So this paper was not as easy to read. I'll put it, I'll say this up. So the language was a bit more complicated, a bit more, let's say, engineering in some way. So it was very, let's say, sprinkled in with a bit more complex explanations, which is not necessarily bad, but just it was a bit harder to intuit the reasons of how this works. But yeah, the main innovation that they have is, look, by using our methods, you can train these NeRF models and also these other models to store information in neural networks a lot quicker by A, with our fast CUDA implementation, and B, using this encoding method that we developed, which is kind of like some hash table encoding optimization.
So what's the difference between this encoding method and the one they were building on?
So the encoding differences between the frequency encoding and this one, right?
Yes.
So I'll also bring this up. So in addition to this frequency encoding, so after like frequency encoding that the original paper did, then people also got, let's say, very beautiful pictures using something called parametric encoding, where like, I think they are trying to train for this basically encoding. So in some way, as we described, these like transformers, where you have trainable encodings, they also had like some extra parameters that you train for that describe how you encode the space. So, and you can do like, then you can do different ways of how you have these parameters, but in essence they were called parametric encodings. But now these parametric encodings, they have some, let's say, problem cases. You make it once again a lot slower to get these, to find these new parameters, and you also add, for like, you do additional parameters. They mentioned that there is a larger memory footprint for smaller computational cost, but I think that was mentioning this one already, like a specific, or what, or is it actually? I'm not. I'm not 100% sure if it is it like a. How do I put this? Are the extra parameters less than the higher dimensional, let's say, feature encoding or not? It seems from that, from this description, that the memory footprint is smaller, but the computational cost is still lower.
That is a trade-off that is usually done.
Yeah.
Because the output was quite small. It was like a few megabytes in the original paper, I think.
With playing with Instant NGP, main annoyance was because that my GPU didn't have a lot of memory, so I was not able to make a video for how it worked, because when I tried to run OBS, then good out of memory, and I did not have enough time to figure out, maybe if I reduce a few images, maybe, and so on and so forth. I also was limited by the amount of images I had. So initially I took, let's say, 140 images or something like that, and that was too many. And I had to reduce like 30 images so I wouldn't run out of memory. So that was interesting. I think it is a combination of the methods used and my GPU not having that much memory. So it has 8 gigabytes for reference for anyone who is interested. Yeah, but so that was kind of where one direction of these NeRFs went. So parametric encodings that you basically you somehow train for this encoding function instead of having, let's say, frequency encoding or something like that. But still, encoding to higher dimensional space is very important. But now, what if we use the same thing as transformers do? We try to find what this encoding is, so we learn it. Then they described a bit of different ones. Then they mentioned sparse parametric encodings that although although you get greater accuracy, you lose efficiency, so training takes longer, etc. So finally they come up with something that so they also mentioned that these parametric encodings, the way that they are usually used, they require a lot of kind of custom. Where did they mention it? I think somewhere here, also maybe lower. It's really hard to scroll through papers and be like, where was this thing? At least for me, my memory doesn't work like that very well.
So this is on our side. It's we have to be better at.
Yeah, I need to start, for myself, need to start making some line numbers or something like that, or page 3 bottom side or something like that. I'll keep that in mind. But yeah, there should be somewhere here.
The most fast.
Yeah, well, they start talking about this same point that we did before. That if you have like the no encoding, you get poor approximation of light field. If you do frequency encoding, you get more accurate. There should be there is this picture here also. Yeah, so frequency. So dense grid is this parameter grid. So this is the C. So from here you get dense grid of interpolated 16-dimensional feature vectors that basically do this encoding. So this is this parametric encoding. Now, if you have multi-resolution dense grid, this means once again that you have grids with different resolutions, and this is basically gives you this higher frequency and lower frequency, and you basically not everything is this very fine parameter space. And then their method
Is the
where
is the fastest and the best.
yeah, it's the fastest. But yeah, fundamentally they have a very interesting way of describing their kind of encoding method, which I struggled a bit with. So they mentioned these parametric encodings require a lot of I think it here it mentions that it might the parametric encodings might require pre-existing knowledge about the space or stuff like that. So here I'm once again like unsure like how they build up this structure of these grids and stuff like that. But yeah, but they basically propose a method that is, let's say, foolproof. So they have like some hash functions where they basically encode informations into, let's say, smaller and smaller chunks, and then they train these, like say, they use these different, like this abstract hash encodings to kind of, in some way, it is similar to having, let's say, smaller and smaller spatial grids. But because they do it with these hashes, they are able to make it computationally super efficient. So that is their, like in some way, that is their main, let's say, objective of using this method, is that they are able to make this computationally super efficient. I was not able to figure out if there is any other, let's say, analytic reasoning why to do this. But they also mentioned that because their hash tables, the way they work, because they're that efficient, and they don't deal with any, let's say, conventional hash table problems, so they don't deal with collision stuff like that. So if let's say one kind of hash points to two different, or if let's say one hash is accidentally used for two different points in space, so their hash table is not, hashes are not very large, so this might happen, like collisions might happen, then they just say, but this doesn't matter because it is unlikely that this collision happens between important points and not important points. So if the hash collision happens between points that is in open space and on the image, then it doesn't matter because the kind of gradient descent still uses all the relevant information about this hash function still is applied correctly because of this how we actually find this final pixel value. We use this framework, like you use actually this volumetric rendering, and if there's nothing there, then it doesn't matter because the opacity is zero pretty much. So the hash table is pretty much just a very computationally efficient way on how to how to put this to encode this space in smaller and smaller kind of like not dimensions, but you could say frequencies, I guess. Well, in smaller and smaller, let's say, discrete steps is how I understood that. Does that make sense to you?
Sure.
You sound confident.
Very not confident.
Yeah, but I am also not very confident in the general hash encoding thing, because they also kind of how do I put this? They did not present this motivation to me very well. It looked more like in some way that it's very, let's say, GPU friendly. They describe this part quite a bit, so that they are able to make the hash encoding stuff very fast. And I would say that they present the results also from the point of view of, if I go back to this, here was this different encoding methods compared to each other. Here you can already see that pretty much visually, so all of these results are for some amount of training time, pretty much. And especially this information comes out in this this table, which I'll zoom in a bit for. So the values that you have, the quote unquote higher is better. That means that what was the exact? I think it was it some loss or something like that. Lost decibels. They don't mention it here under the figure, unfortunately. But as far as I remember, it was lost decibels. It's not here anywhere, right?
No, don't see.
Anyways, higher is better means in their formulation, it means that there is less difference between the input images and the generated images by the neural radiance field. And it's on a logarithmic scale, so it's not, let's say, linearly better, but it's on a
PSNR.
Yeah.
Peak signal to noise. Everyone likes peak signal to noise ratio.
Yeah. And now the main point here is that they're, let's say, they train both this with their hash and with the frequency, and they show what you can do in, let's say, with training these methods in this amount of time. So if you look at like the space NeRF paper, and then there are some innovations. So NS, VF, and MIP NeRF, which I also have seen a bit about. So they, if you look at this original NeRF paper, you for different scenes, you have this value, and then they show that, for example, with this hash-based encoding function, they are able to achieve a very similar result in 5 seconds as the original NeRF paper was able to do with hours. And they also show that this hash thing is very like outperforms the frequency encoding a lot, especially like speed wise. So in, let's say, if you do the frequency encoding, even if you use all the CUDA good things, then with 5 minutes you are able to get similar performance or similar-ish performance as with this 5 seconds of this hash encoding. And the results, if you look through the scenes, the results are relatively consistent with each other. They are not able to get as good pictures in many cases as some of the other algorithms, but at the same time, if you look at this, but it depends a lot on the scenes. Still, so in some scenes they are able to do even better than some that was in some state-of-the-art done in hours, but theirs in theirs is able to do that in 5 minutes. And here they also mention that the once again here somewhere they mentioned that this frequency encoding is likely to still reach like a lot better performance if they would let it run longer, pretty much. Yeah. So in this, like overall, it's a very great library to use for people. I think for me it was more important to bring this out, not as like a great paper or, let's say, very significant paper results, but more for people to just pick it up and use it. And I'll just show a couple of images where I basically took. Unfortunately I'm not able to show a video because my, once again, video card ran out of memory. But I would like to point out some important parts. I'll actually zoom in on the left part here, which I think was the most important thing actually, is
The
that
training seed.
Sorry?
The training seed.
The training seed was given by that was not me. That was the initial one, so props to them for that. But the UI interface for training testing was incredibly good, like absolutely incredibly good. So you just run the setup was very quick and everything just worked. But you are able to pretty much change the what you want to train for. You are able to train for extrinsics, exposures, distortion, so the internal parameters of the camera. You can toggle this on and off during training, and it changes what it is optimizing for. I thought I did, but I didn't, I guess, open up the NeRF training option, so I have to talk about this on my own. So under the training option, so you can choose patch size and stuff like that here already, but under the training options, you can choose activation functions, loss functions, stuff like that, basically, just from this menu, which is great. You can reset training, you can snapshot your current training results and start, let's say, train from there, and so on and so forth. You can use DLSS for rendering. Once again, ran out of memory. It wasn't able to do that. Change the target FPSs and so on and so forth. So there is like a lot of graphical user interface enabled features to change how you actually are training this already.
It seems it only takes like 6 gigs of memory in the top.
Yeah, and my computer took a bit, and I stopped training in between. So the 6 gigabytes of memory is render only, because I stopped training the network, so I was able to actually make better resolution images. So zoomed in a bit. Now you see some interesting deformations and stuff like that, because on this picture I accidentally or on purpose, let's pretend it was on purpose, changed stuff in this view on the image, and it was very interesting what happens with let's say, so this, in some views the chair is here, in some views it is not, in some images. So it generates, let's say, opacity for this chair in some specific, let's say, configurations, which then creates some interesting, let's say, so that it would match the couch on the background. So this is like opaque here, and stuff like that kind of comes out. So it is quite and unfortunately, I didn't find any like filters for opacities and stuff like that. It would be quite interesting to filter out some stuff from opacity, especially for making these, let's say, very rigid scenes. But yeah, it was very interesting to see how it performs in stuff like that. And you can get like, but let's say, especially watching from kind of your own computer and looking it through in a 3D structure and moving it around there smoothly, it was very impressive. So yeah. I guess that's it from that part. I also put links to kind of for more NeRF stuff for the future for ourselves and for anyone who is interested in the topic. Frank Bellart has cool blog posts about the status update of NeRFs in these different conferences and what the different innovations have been.
I will put them in the notes of the, under the YouTube video then.
Yeah. NeRF. But overall, that's about it for the content cool. Here.
It seems very useful for like, because I mean, there's also the photogrammetry companies that like image stuff for video games, where they go make 1,000 pictures for stone. So I guess that can a bit streamline that process most likely, unless they already had this and they never talked about it, because I mean it's a private company. So
yeah. But yeah, like the library, the quality of this kind of thing from let's say doing almost no work to set it up was quite impressive to me. You didn't need like you were able to actually not just once again you were able to use it on like your own pretty crappy, for my case, video card to get, let's say, these NeRFs running. So I think it definitely shows that this thing has like potential to scale for different applications. I'm quite interested in what it can do in like simultaneous localization and mapping stuff, where there are a few papers already. And of course, well, computer games, whatever. Just hobby interest also.
But yeah, I think that's. Do we have something nice to say for the conclusion?
No, but this was
No.
a cool topic. Cool topic. That's about it.
It seems Henrik is likes this topic a lot, so most likely we're gonna do it again soon on the next papers. So not next week, 'cause then it's my time.
Like,
I have some ideas, but I'm gonna choose soon. So nothing specific as of yet. So hopefully we'll be live again on Sunday. If not, then the Sunday after that. If not, then at least within a month. but we'll try to keep it like once a week or bi-weekly.
Yep.
Not bi-weekly, I think. No.
Depends.
Anyway.
There are two ways of bi-weekly, and different cultures use different meaning of the words.
Okay.
One of those.
But thanks for listening to us. So yeah, see you again in